Page 13 of Euler's complex numbers, which is chapter 16 of MHL. 16F, roots of complex numbers, page 500 reading. We have raised complex numbers to the nth power using de Moivre's. Now use it to find roots. Okay, so now we're kind of going backwards. So we're going to solve z to the n equals c, where n is a positive integer and c is a complex number. If c is a real number, then the complex roots will occur in conjugate pairs. Okay, that's something that we kind of known before, right? That like if you multiply conjugate pairs together, you get real numbers. So kind of makes sense that if you're looking for roots of a real number, then the roots are going to be conjugate pairs if they're complex. If c is not a real number, then not all the complex roots will occur in conjugate pairs. Okay? Modulus of all the roots will be the modulus of c to the nth root. On an argand diagram, all roots will lie on a circle of radius r equals modulus c to the nth root. The roots will be equally spaced around a circle. Joining the points will form a regular polygon. Easier than factoring, the nth roots methods requires you to write c in cis form. Add 2 pi k to the original argument of c before applying de Moivre's. Okay, so let's do a simple example here, and then I think you'll understand better how this works. Find the 3 cube roots of 1 using factorization. Okay, so if we write the equation z cubed equals 1, this is basically stating that z is a cube root of 1. And the most obvious cube root of 1 is 1, right? So let's write it as a polynomial. Equal to 0. And then we're going to use factorization to solve it. So z cubed minus 1, we know that one of the roots of z cubed minus 1 is 1 because if you put 1 in here, it works, right? So how do we find the other roots of z cubed minus 1? Well, synthetic division. So basically z cubed minus 1 is a polynomial with 1, the coefficient 1 for the z cubed, the coefficient 0 for z squared, the coefficient 0 for z, and the coefficient negative 1 for the constant term. And we know that 1 is a root that works. So we're going to do synthetic division. And we find out that we can factor z cubed minus 1. If we break it up into z minus 1, we break it down into a quadratic where it's z squared plus z plus 1. And that is equal to 0 too. So we know that this orange part is equal to 0 also. And those are going to be complex roots, but we can find them easily by using quadratic formula. B squared minus 4 times a times c. And a and c are both 1, divided by 2a. So we're left with negative 1 plus or minus square root of negative 3 divided by 2. So negative 1/2 plus or minus I times square root of 3 over 2. Okay, so if I was to graph the root z equals 1 and these two roots here on the unit circle, or not necessarily the unit circle, but on the complex plane, I would see that 1 would be here, negative 1/2 plus I square root of 3 over 2 would be here, 60 degrees in that direction, okay? And negative 1/2 minus I square root of 3 over 2 would be 60 degrees in that direction. So you can see that they trace these three complex roots, they trace a unit circle. They're all 1 unit away from the origin, and they're just pointing in different directions. And you can see that the angle between all of these roots is 120 degrees. So pretty neat, huh? Okay, let's use the nth roots method instead. So with the nth roots method, what we're going to do is we're going to apply de Moivre's. So z cubed equals 1. And remember, in the instructions it says to add 2 pi k to the original argument of c before applying de Moivre's. So our original c value is 1. So instead of 1, we're going to write 1 cis, and normally 1 is cis 0, right? We're going to write cis 0 plus 2 pi k. And that's equal to z cubed. Then we're going to say, instead of z cubed, we're going to write z equals, and we're going to take the cube root of the other side. So it would be 1 to the cube root times cis 2 pi k to the cube root. And that would mean z equals 1 cube root is just 1. Cube root of a cis is equal to cis, and then we just put the exponent inside. Cis 2/3 pi k. And so let's start with k equals 0. If k equals 0, one of the roots is 1 cis 0. Another root is 1 cis 2/3 pi. And another root is 1 cis 4/3 pi. And you can see that these three roots, which is 1, and this would be negative 1/2 plus I times square root of 3 over 2, and negative 1/2 minus I square root of 3 over 2 is the same as the roots we found over here on the left. Okay, let's do number 2. So we got z cubed equals negative 8i. Negative 8i is the same thing as 8. It's like a vector pointing down in the complex plane, right? Negative I. So we could put 8 cis pi, or cis negative pi over 2, or 3/2 pi. Which do you prefer? We'll do 3/2 pi. Okay, so we'll do 8 cis, I'm sorry, I forgot to write the left side. Z cubed equals 8 cis 3 pi divided by 2 plus 2 pi k. And then we're going to cube root both sides, so we get z equals, and the cube root of 8 is 2, and the cube root of a cis 3 pi blah 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 looks like that. And then we'll simplify it. We're going to put the 1/3 inside here. So we're going to get 3 pi over 2 divided by 3 is going to be pi over 2 plus 2 pi k divided by 1/3 is 2/3 pi k. So one of the roots is going to be 2 cis pi over 2. And that's if k equals 0. And if k equals 1, it would be 2 cis pi over 2 plus 2/3 pi, which would be 5/3 pi. So if I add together pi over 2 plus 2/3 pi, I get 3/6 pi plus 4/6 pi, which gives me 7/6 pi. Okay, and then finally, if I take 7/6 pi and I add it to 2/3 pi again, I'm going to get 7/6 pi plus 4/6 pi, which is going to give me 11/6 pi. So it'll be 2 cis 11/6 pi. And so that would be the 3 roots in this case. Find the cube roots of -1 and display them on an Argand diagram. So that would be z cubed equals -1. So remember that z cubed is equal to, let's see, -1 is equal to 1 cis pi. And I am going to write, instead of 1 cis pi, I'm going to write cis pi plus 2 pi k, where k is an integer. K is any integer. And I am going to take the cube root of both sides. So I get 1 to the 1/3 power, which is 1. And then I can take the argument here and divide it by 3. And I get that. And so I have 3 roots, and one of the roots is pi over 3, and the other 2 roots is pi over 3 plus 2/3 pi, and pi over 3 plus 2/3 times 2, which is 4/3 pi. And so the pi over 3 is one of the roots. I'm sorry, cis pi over 3 is one of the roots. And then cis pi over 3 plus 2/3 pi is one of the roots. So that would simplify to cis pi. And last of all, cis pi over 3 plus 4/3 pi is same as cis 5/3 pi. And so my 3 roots are pi over 3, pi, and 5/3 pi, and it says to draw them on an Argand diagram. So pi over 3 is 60 degrees, so it looks kind of like this. And cis pi is 180 degrees, it looks kind of like that. And 5/3 pi is like 300 degrees, so it kind of looks like that. And all of them are 1 unit away from 0, the origin. So it kind of makes a circle. All right, and that's the way when you map roots on the Argand diagram, they look like that, right? They're like equally spaced spokes around a little wheel. Okay, z to the 4th equals 16. Z to the 4th equals 16. So 16 is equal to 16 cis 0, 0, which is equal to 16 cis 2 pi k. And z is equal to the 4th root of the right side, and the 4th root of 16 is 2. And the 4th root of cis 2 pi k is cis 2 divided by 4 pi k, which is equal to 2 cis pi k pi divided by 2. And there are 4 roots here, so we'll start with k equals 0. K equals 0 will give us 2 cis 0. And then k equals 1 will give us 2 cis pi over 2. K equals 2 will give us 2 cis pi. And k equals 3 will give us 2 cis 3/2 pi. And then let's draw this on the Argand, even though it doesn't ask us to, let's draw this on the Argand diagram just to see if we got the right answer. So there's 0, there's pi over 2, and there's 3/2 pi. So yeah, it worked, didn't it? 5. Find the 4th roots of -I and display them on the Argand diagram. Okay, so this is not a real root. Z to the 4th equals -I. -I can be written as 1 cis -pi over 2, or we could say 3/2 pi, okay, but I'm going to put -pi over 2, plus 2 pi k. And since it's z to the fourth, I'm going to say z, I'm going to take the fourth root of both sides. So the fourth root of the modulus 1 is just 1. And the cis value is going to be negative pi over 2 times 4 plus 2 divided by 4 pi k. So that would be cis negative pi over 8 plus k pi over 2. And if k is 0, then the first root would be negative pi over 8. And the second root would be k equals 1, so that would be negative pi over 8 plus 4/8 pi, which would be 3/8 pi. And the third root would be negative pi over 8 plus pi, which would be 7/8 pi. And the last root would be negative pi over 8 plus 3/2 pi. 3/2 pi, if I make it over a common denominator of 8, would be 12/8 pi. Minus 1/8 pi would be 11/8 pi. Okay, so like between each one of these is 4/8 pi, 4/8 pi, and 4/8 pi, so they look evenly spaced. So let me draw this. So negative pi over 8 would be like 22.5 degrees, kind of down here, I guess. 3/8 pi would be kind of like that. 7/8 pi would be kind of like that. 11/8 pi would be kind of like that. So this is an example of 4 roots to a complex number, not a real number. So they are not conjugate pairs, right? They're just kind of like in whatever direction, but they're evenly spaced out as usual.